Thank you, Trish. Gracias a Maria. Thank you to everyone. Thanks to the band. It's great to be here and to share with you this journey. We've all been hearing about AI. Some of us have heard about quantum. Who's curious here about quantum? Okay, we have most of the audience. Okay, hopefully by the end, everyone will be curious how AI and quantum will help us. AI and quantum can work together in a synergistic way to really impact our lives, and we'll talk about that impact. We're going to go on a journey now together for the next 15 minutes about how these two work together. Quantum and AI is not just about computing. Yes, you've heard about quantum computing, but quantum is so much more than that, and we use AI in every single aspect of quantum technology to really bring it out and bring the impact out. Let's start with ourselves, the human body. We're trying to understand the human body. We want more medicines to make sure that we have medicines for treatment of our diseases out there. And so what can we do with AI and quantum when it comes to this very, very important sector? Well, right now, the system is broken. Right now, if you have a molecule and you want to make it into a medicine, on average, it takes about 13 years, takes about 2.5 billion euro, and the failure rate is still upwards of 70%, even with all that money and all that time that you put in to trying to make that medicine. Medicines for cancer, medicines for Alzheimer's, medicines for Parkinson's. These are critical issues right now, and we don't really have any good treatments for many of these diseases. We have to change the system. AI, working with quantum, can do that and has already begun to do that. So how does that work? Well, if we have, for example, our body and we enter something into the blood vessel, say this chemical here, this molecule that is anti-cancer, we want to understand what the interaction is of this molecule and our body. Normally what happens is we do the best we can in the lab, and then we introduce it to human trials. Phase 1, phase 2, phase 3 human trials, and again, 70% of the time it fails. How can we actually understand the interaction of these molecules with our body before it goes into humans? This is the world of quantum mechanics. The language that molecules speak to each other when a molecule meets our body, that is governed by the laws of quantum mechanics. That's why we must use quantum. AI is very helpful, but only when you have big data sets. By definition, when we're going for first-in-class molecules, first time to really treat a key disease, we don't have big data. We cannot use traditional supervised learning or even self-supervised learning. We need to work from first principles up using quantum mechanics itself. Here's another molecule that everyone, I'm sure, in this room has ingested today. Anyone want to take a guess? What is this molecule? Did anyone have coffee here? Caffeine, correct. So this is caffeine, which also impacts our body. Studies happen about how it interacts with our body, positive, negative. This is all, again, governed by quantum mechanics. So we can bring AI and quantum together. We can bring them together to understand how these molecules interact with our bodies, be it vitamins and supplements or prescription drugs, before we have 13, 14 years, 2.5 billion euro, and ultimate failure. We must do better, and we can do better with these tools. We are the first generation of humans to be able to harness not only the power of AI, which is even just now at a beginning stage, AI inspired by our brain architecture itself, we're now just beginning to see some of the larger impact. We're also, though, the first generation to really harness the quantum world, to be able to, at scale, do these computations. These kind of computations were not possible even 2-3 years ago. We did not have the computing power on this planet to do that. And so now that becomes possible. We're now in the third quantum revolution. The first revolution was 100 years ago, mainly in Europe. A number of key people, Schrödinger, Dirac, Einstein, Bohr, many others, Marie Curie, inventing and discovering the laws of quantum mechanics, the laws of our universe. Second quantum revolution in the 70s, 80s, 90s, harnessing the power of quantum to give us MRIs, to give us all these great tools. And now we're in the third quantum revolution where we can take more advanced technologies and bring them to the market, bring them to the clinic, bring them to the hospital, bring them to clean energy. If you're interested in clean energy, then we're interested in batteries. Batteries to power electric vehicles, batteries to power storage of renewable energy. Here in Spain, there's quite a bit of solar and wind energy. How do we store that energy? The current chemistries do not scale very well. Quantum and AI together, we can simulate and we can drive that forward in ways that we could not before. So, the past 75 years of computing have been in the upper left quadrant you see over there. Classical data being processed by classical processors, CPUs and GPUs. We're now entering a new era, these other quadrants where we can take classical information and also process it now in new kinds of processors. And this is going to be a hybridized, mainly cloud-based initiative. CPUs, GPUs. People here know what GPUs. What does GPU stand for? GPU? Anyone? What's the G? Graphics, right. Graphics processing unit. These are the GPUs that are powering the AI revolution you're hearing about right now. All the LLMs, the chat GPTs, these are being powered by these new GPUs. What's the graphics in there? Well, the graphics there is because they originally started by helping create video games better. So every time you see a kid playing video games, thank that kid, because that GPU is what's now powering the AI revolution and now also this AI plus quantum revolution. And eventually we'll have the QPU as well. And these are some of the impact areas that working together, classical and quantum, will be able to impact. And these quantum computers use qubits, quantum bits, instead of just bits, having a bigger representational area. There's a lot of ways to build these quantum computers. We don't build them the way we do traditional computers. And these are some of the examples. You can use light on the lower right. You can use superconductors in the upper left. Many ways to build it. And many companies around the world right now are pursuing this. There's an EU flagship initiative right here in the European Union that is focusing and investing in these kinds of technologies. But although quantum gives us many new capabilities, it also means danger for encryption. Danger for encryption, because the encryption in all of our phones, when you connect with your bank, connect with all your different companies, that encryption will be broken by quantum computers as well. And so right now there's an attack happening where adversaries, hackers, are storing your information, storing the information of governments, of companies. They can't read it now because it's still encrypted, but in a number of years they'll be able to read it with their quantum capabilities. And so what tools do we have? My team put this in, I think they think it looks like me. What tools do we have to address this? Well, we have two main tool sets. PQC, post-quantum cryptography. These are new algorithms tested over the last 25 years. All the phones in this room, all the servers, all the laptops will be migrating to post-quantum standards over the next 5 to 6 years. Every single app, every single phone, every single computer will and must migrate to these to be safe against this attack. And so, although Shor's algorithm, which runs on quantum computers, is the one that breaks quantum, the good news is we now have algorithms that can be implemented on your current phones, current laptops, servers, clouds, in order to protect against this attack. So a lot of people put a lot of work into that, and next time you think about mathematicians, thank them because they had a large part to do with that. And if you're more interested in that, you can read our paper in Nature describing that issue. Another way to also protect it is with the quantum intranet. I won't spend much time on that, but if you're interested, this is a fascinating area. We use protocols like quantum teleportation. We are not teleporting people. Sorry, Jose, I know Jose has been with me at the Singularity University. We're not yet there at teleporting people, but we do teleport data, and we read it left to right the way we do a musical score. Any guesses what this musical score is from? What famous Beatles song? Any musicians here? Okay, it's Let It Be, which is one of my favorite songs. So we read it left to right, and we do operations just like we do in music. We read it left to right, and we do operations on the qubits in that way. So now let's talk about quantum sensing. We talked about quantum computing. We talked about its positive effects and also the fact that it's going to break encryption, but we have a solution to that. We talked about quantum networking, connecting quantum computers together. And now let's talk about quantum sensors. Quantum sensors are here today. They don't need error correction. They don't need scaling. They're here right now. This is an example right here of a quantum diamond. It's a diamond made right here in labs around the world, not taken from mines. We make it in such a way that we can lift the electrons to higher quantum states, and that gives us a great way to detect the magnetic fields around us. One application is for heart disease. Right now, in a medical center in the States, we have a device right now that is detecting heart conditions and diseases using the magnetic field, MCG, magnetocardiography, instead of ECG, electrocardiography. And so this is an example where you need a quantum sensor because the magnetic field of the heart is so weak so feeble that you need a really good sensor to detect how that magnetic field is telling you the condition of the heart. So back again to the big picture, the CPU, the GPU, the quantum processing unit, this is our future in a hybrid cloud. These GPUs, as I mentioned, are leading to tremendous uplift in terms of the emergent properties of LLMs. We're all experiencing that right now, and it's very, very exciting. But we also have eRoom's law. People here know Moore's law, which is that things double every 18 months, but now we're in a reverse. eRoom is Moore's law backwards. Because unfortunately, as we make more and more powerful models, they're taking more and more compute time. If we could just go back for 1 second, you can see that, see here, yep. You can see that GPT-4 is rumored to be about 1 trillion different artificial neurons in there. Palm from Google is 540 billion neurons, artificial neurons. So these language models are getting bigger and bigger and bigger, and the same also on imaging and video. And so we really want to think about how do we handle this kind of compute? How do we manage this kind of compute going forward? This is going to be a major challenge, both for the compute and also for the carbon footprint that it entails in running all these servers to make all these things happen. So one of the key objectives I put out as a challenge to my colleagues in the AI community is not just let's make bigger and bigger models, but let's also make more efficient models. And some recent research is showing that actually if we train the models, smaller models on smaller amounts of data, we might actually get great LLMs with less hallucination, with less of the false information coming out of it as well. So, explosion happening, everyone is aware and trying that out, but it's not just LLMs. We need to also look at other tools in the toolkit that are happening right now. All kinds of reinforcement learning, computer vision, machine vision, applications and looking at radiology and all kinds of other healthcare applications. I am personally very excited about the education area. To me, when people ask me about AI and they say, are you worried about it? Are you excited about it? What's your opinion on the explosion of AI? I say 2 things. First, education. I put out a challenge to all of us to say, how can we use AI to redo education, to rethink education? We have failed. We have failed in the US, we have failed in other countries, in K through 12, in the world of education. And it's a matter of giving teachers now the training and the tools to think about education in a more personalized way for each child. Some children like to learn with video, some with text, some with audio, some with interaction, some on their own, some in groups. AI can help facilitate that. So we need all the teachers and we need to train them. And I called quite a number of schools that we're involved in as AI was getting bigger and bigger and said, please, do not go to your reflex to ban this, to stop using this in the school. Go to another idea, which is let's use this to bring the creativity of kids out. Kids can be very creative with these tools, and we can empower them with these tools. And I'm happy to say that a number of the schools are now doing that, but we need to do that all around the world. Agriculture, finance, these are 2 other areas as well. One trend that you'll start to see more in the next 36 months is embodied AI. Robots and other devices that have AI built into them that we can interact with in the physical world. One of the best applications that I'm excited about there is in hospitals, healthcare, nursing homes, and other applications to take care of people. Right now, we have a shortage of people here in Spain, in the US, all around the world, in hospitals, in clinical care. Robots can serve a key value function in that particular domain. And so that's a very, very exciting area. The one thing I'm worried about AI, if people are interested to know, is not Terminator AI. It's not a dystopian future. It is what I call adolescent AI. And so we have to worry about giving AI too much responsibility too early. And I think that many people now are thinking that. So to sum up, neuroscience still has a lot to teach us about AI. There's a lot that we can learn there. We're doing a lot of investment at our group, Sandbox, to invest in the future and training people here in Spain and all around the world. And I welcome you to join us. You can check out our website with lots of code and tools and slide decks to join us in this revolution of AI and quantum. Thank you very much.